in this molecule, that little stick holding those two atoms together is the covalent. Here's a water molecule. You've seen that before, and that's the proper term, molecule. Have you ever seen one of these models? Well, we're going to learn about covalent bonding and molecules in today's lesson. So let's get going. Remember about the other way of bonding. That would be ionic bonding, and that is ionic compounds. So I'm just going to put the words down for you. Ionic bonding is, the key word is transfer, and we have cations and anions and the electrical attraction between those. Okay, that is the ionic bond. There's nothing more than static electricity holding ionic compounds together. Okay, hold on to all of that and let's switch gears. Let's go to covalent bonding. So remember why things bond: to become stable. So we've already talked about gaining or losing. That's the ionic situation. But the sharing thing is what we're going to talk about today. If you share electrons to get your octet, then you will form covalent bonds. And a covalent bond, the bond is nothing more than a shared pair of electrons. Okay? And so take a look at this structure. In this molecule, that little stick holding those two atoms together is the covalent bond. And I must admit that when I was a kid, I thought that molecules were held together by little sticks. I thought that was really a thing. It's not. It's just a model representing a pair of shared electrons. So when you see this model, this is a molecule, covalent bond, a pair of shared electrons. Now, a molecule, we're going to use that word only when we're talking about covalently bonded structures. So don't use the word molecule with ions. Those are separate things. So this is a molecule. Molecular formulas work the same way. We've got subscripts that show how many of each type of atom are bonded together. Now, this is a little table that is trying to distinguish between ionic compounds and molecular compounds. And in chemistry, that one of the first things you have to think about is this ionic or is it molecular? And so this is the contrast. How do you know? And this is probably a good little table to memorize. If you have a metal and a non, or polyatomic ions, that is going to be an ionic compound. However, if you have two non-metals bonded together, and remember where metals are on the periodic table, it's that upper right triangle, if you will, corner, those are non-metals. If they're bonded together, then you have a molecular compound. The contrast in electrons is, are they transferring or are they sharing? See, molecules are nicer. They share electrons. Cations and anions for compounds, there are no charges. Do you know why there are no charges in molecular compounds? Because there's no transfer of electrons. There's no imbalance of electrons. Physical properties vary as well. One of the most significant differences is the melting point and boiling points of ionic and molecular compounds. So keep this little chart handy. It will save you in the future. Now, most important of all, you've got to be able to identify the number of valence electrons in any element. So let's just go over this one more time. These guys in this group all have 1, 2, and the whole group. Skip the transition metals. You won't need to know those. 3, 4, 5, 6, 7, and 8. Except for little helium. Little helium only has 2 electrons. And he is a noble gas. You know what? He's already all completely stable. He's got 2 electrons, and that's all he can handle because all he has is his little 1s orbital, and it is completely full. So hang on to your valence electrons, and let's talk about molecules. Here's a water molecule. You've seen that before, and that's the proper term, molecule. And it is bonded together with covalent bonds. Now, remember the octet rule. We're going to share electrons, and we're going to make sure that everybody has the electron configuration of a noble gas. Well, what is that number? 8, except for hydrogen. So let me show you how this works. Hydrogen sees 2 electrons. That little stick is going to represent 2. This hydrogen thinks he has 2, so they're good, they're stable. And then the oxygen has 2, 4, 6, 8. So the octet rule is satisfied.